Hi everyone, today we will be discussing microelectromechanical systems or MEMS and their role in the field of nanobiotechnology. Firstly, what are MEMS? MEMS are miniature devices that combine mechanical structures, sensors, and electronics on a single platform. They allow us to interact with the micro and nanoscale world in precise and exact ways. Let's begin with the fundamentals of how MEMS work. At their core, MEMS operate through two complementary processes, actuation and transduction. These two processes are the core of MEMS technology, enabling us to both control and measure the behavior of their tiny mechanical elements. Think of these elements as microscopic beams, cantilevers, or membranes that can stretch, bend, or twist. The magic of MEMS lies in how we make these structures move, and then how we capture and interpret that motion. Actuation is the first half of the story. It's the process of converting an external signal, whether electrical, optical, or thermal, into physical motion. In other words, actuation is how we push or pull on these miniature structures to make them respond. Transduction is the second half. Once motion has been created, transduction takes that nanomechanical movement and converts it back into a measurable signal. This signal can be electrical, such as a change in resistance or capacitance, or optical, such as a shift in reflected light. Transduction is how MEMS talk back to us, translating their mechanical behavior into data we can record, analyze, and use. Together, actuation and transduction form a closed loop. This loop allows MEMS devices to function as sensors, actuators, and even integrated systems that can both manipulate and monitor the micro and nanoscale world. Now let's talk about actuation. MEMS can use several different techniques. First is the capacitive or electrostatic actuation. This common method uses a nearby gate electrode to generate a driving force proportional to the square of the applied voltage. In the NEMS domain, simple side gates are typically used. This technique is especially useful for materials like carbon nanotubes and graphene, where the substrate can serve as the gate electrode. It's applied mostly in microfluidic pumps and valves for lab-on-a-chip devices. Piezoelectric actuation is a method that relies on the piezoelectric properties of materials such as aluminum nitride. It directly converts an electrical signal into mechanical deformation. To excite bending motion, the piezoactive layer must be placed off-center with respect to the neutral axis. Applications include micropumps for drug delivery, biosensors detecting mechanical forces, and ultrasound transducers for medical imaging by producing ultrasounds that propagate into tissue. Second is the photothermal effect. Here, periodic heating of the mechanical element by a modulated optical field generates thermal stresses that drive motion. This is used to drive soft actuators for biomedical robots and tissue engineering scaffolds. The dielectric gradient force is a technique that uses electric dipole forces that are generated when a dielectric material is placed in an inhomogeneous electric field. The beam is pulled toward the region of stronger field. It's applied in dielectric elastomer actuators as artificial muscles. The optical dipole or gradient forces are forces that arise from field gradients in the electromagnetic field. They allow manipulation of structures and form the basis of optical trapping or tweezers, which are used to manipulate cells, DNA, and proteins. Thermoelastic actuation involves localized joule heating using metallic electrodes fabricated on the resonator. The resulting differential thermal expansion develops a stress field that drives mechanical motion. It's used in thermal microvalves for lab-on-a-chip devices. Last but not least is the radiation pressure. This is the force created when photons strike a reflective surface and transfer momentum, producing a push force. Now let's move to transduction, the process of converting mechanical motion back into a measurable signal. There are several approaches. First is the optical interferometry, or free space. This is a mainstay optical approach, and it senses motion by interfering the light beam reflected from the resonator surface with a reference beam. Applications include biochemical assays and monitoring cell mechanics. Next is piezoresistive detection. This technique monitors changes in electrical resistance due to mechanical strain in the resonator. Microcantilever sensors use this to detect biomolecular binding events, such as antigen-antibody interactions. Next is the optical knife edge technique. This specialized method detects mechanical motion occurring in the plane of the device, which is difficult for standard interferometry. The device acts as a knife edge, modulating the reflected optical signal toward a photodetector. It's applied in displacement sensing for microcantilevers in biosensing platforms. Next is the capacitive detection. This electronic technique measures extremely small changes in capacitance that occur when the structure oscillates relative to an electrode. It's used in capacitive biosensors for detecting DNA, proteins, and pathogens.
To continue, I'll walk through the key fabrication methods used to create MEMS devices. When engineers first started shrinking machines down to the microscale, they realized something surprising. The world behaves completely differently when things get really small. At the micro level, gravity barely matters, as MEMS devices feel almost no weight. Instead, surface forces dominate, meaning tiny particles love sticking to each other. Electric fields also behave differently. Even very tiny applied voltages create extremely strong electric fields. Friction also changes dramatically, such that traditional lubrication, which works perfectly in big machines, simply stops working at the microscale. Because of all of these differences, you cannot just take a structure and make a tiny version of it. Instead, new design strategies are required, rethought around this microscale physics. To understand MEMS fabrication, it's important to know that MEMS were not invented from scratch, but grew directly out of integrated circuit manufacturing, as they use microfabrication techniques such as photolithography, essentially printing patterns using light, oxidation, thin film deposition, and chemical etching. These techniques made it possible to fashion microscopic mechanical parts from or on silicon substrates, which eventually expanded into the main MEMS fabrication techniques, the first of which is bulk micromachining. Bulk micromachining uses the silicon wafer itself as the mechanical material. Silicon is a single crystal, meaning its atoms sit in an orderly 3D arrangement, and crystal materials have a strange property. Different crystal directions dissolve at different speeds. This is called anisotropic etching. Take potassium hydroxide as an example. It will dissolve some silicon planes quickly and barely touch other planes. So if you place a patterned silicon wafer into potassium hydroxide, the etchant naturally will form slopes and cavities at well-defined angles. But engineers don't just throw the whole wafer into acid. They first add protective layers like silicon dioxide or silicon nitride and use lithography to choose exactly which regions get exposed. So the rule becomes exposed silicon dissolves and masked silicon stays solid. This lets engineers carve out things like diaphragms, pressure sensor membranes, beams and supports, and pits and cavities. The next technique is surface micromachining, which works in the opposite way. Instead of carving down into silicon, we build mechanical structures on top of the wafer, using layered thin films. The figure shows the standard process. Deposit a sacrificial layer, usually silicon dioxide, which defines the gap beneath the moving structure. Then deposit the structural layer, usually polysilicon, which becomes gears, beams, combs, drive, etc. Next, we pattern the structural layer using photolithography, and finally, release the structure by dissolving the sacrificial layer in a chemical bath. This frees the mechanical parts so they can move. This technique allows for smaller structures, smaller footprints, and tighter tolerances. The next technique is LIGA, which stands for lithography, electroforming, molding. And the figure illustrates its three-stage process. It begins with deep X-ray lithography, which carve out thick PMMA resist, a thick plastic layer that X-rays can shape, and generates tall, perfectly vertical features, something optical lithography cannot do. Next, the tall cavities are filled with metal, often nickel, using electroforming, a process where metal is deposited into the patterned holes to form the final microstructure. Finally, the resist is stripped away, leaving a high aspect ratio microstructure with extremely smooth sidewalls. Finally, let's talk about MEMS bonding. Although bonding doesn't create mechanical structures the way bulk and surface micromachining or LIGA do, it is critical for turning 2D layers into functional 3D MEMS devices. Many MEMS devices cannot operate without things like sealed cavities, vacuum environments, or multi-layer stacking that require bonding to make possible. The first bonding category is direct bonding, which requires extremely flat, extremely clean surfaces. The first technique is fusion bonding, which joins two silicon wafers by heating them until the silicon atoms at the surface merge into a single lattice. Anoidic bonding, which is depicted by the figure, bonds silicon to glass using heat and a strong electric field, causing ions in the glass to migrate and form a permanent seal. Finally, laser-assisted bonding heats only the bonding interface with a laser so the wafers can join without heating the entire substrate. The next category shown in the next figure is intermediate layer bonding. Instead of relying on perfectly clean surfaces, these methods use a thin bonding material between wafers. Glass frit bonding, shown in this illustration, where the glass powder is melted to form a seal. Eutectic bonding, which uses alloys like gold silicon to create a strong metallic bond. And polymer bonding, using materials like epoxy, which is useful for low temperature processing and to create flexible seals. Now, comparing the main fabrication techniques, bulk micromachining produces deep, well-defined 3D structures with clean anisotropic sidewalls, and it has a very high mechanical stability because the silicon wafer itself becomes a mechanical material, but the geometry is limited by the crystal lattice. Surface micromachining offers more design freedom because you're building with deposited layers and not relying on silicon crystal planes. It produces compact, high-density structures, but the devices are mechanically weaker and more vulnerable to stiction, especially during the release process. LIGA occupies a league of its own as it provides unmatched height, aspect ratio, and dimensional accuracy for structures such as gears and mechanical assemblies, but it is costly and requires specialized equipment. The bottom line is that there is no single best technique. Each method fills different parts of the MEMS design space, which is why real MEMS devices often combine multiple techniques to achieve the required geometry, performance, and manufacturability criteria required.
Now I'm going to be discussing the advantages and the weaknesses. First, let's talk about why smaller is actually better. When you shrink components to the microscale, you start to need way less material. That cuts manufacturing costs and makes production incredibly sustainable. The semiconductor industry has spent decades perfecting batch manufacturing at this scale, so the MEMS can basically piggyback on all that expertise. But here's what makes it really interesting. At the microscale, the physics changes. Surface forces such as friction and adhesion suddenly become dominant. In everyday world, these forces barely matter. But here, they completely reshape how things work. The genius move is that now you can build electrical and mechanical components on the same chip with incredible precision. That means complex, multifunctional devices can be mass produced reliably at scale. And there's something really recent that's been game changing, which is optical actuation. Instead of physical mechanical connections, researchers now use patterned light in order to drive MEMS components. You can spin silicon gears smaller than a human cell without any physical contact. For biomedical work, that's huge. You get precision control while staying minimally invasive. MEMS enable microfluidic lab-on-chip systems, optical sensors, targeted drug delivery, and incredibly sensitive biosensors. Because they operate at the same scale as cells and molecules, they can achieve precision and sensitivity that larger devices just can't match. And this is the versatility of these devices. Now it's time to discuss the weaknesses. First, the tribology nightmare. So MEMS face some serious challenges, of course, and the biggest one is stiction, where surfaces stick together permanently. At the microscale, van der Waals forces, capillary forces, and electrostatic attraction all kick into overdrive. These forces are nearly impossible to eliminate, and they can cause moving parts to fail before the device even starts to operate. Add in fact that classical mechanics doesn't quite work at these scales, and you start dealing with material challenges that don't have easy answers yet just yet. Manufacturing itself is tricky. The release process, where you dissolve sacrificial layers to free up moving parts, often causes stiction damage right away, and these structures require nanomaterial level alignment. Even tiny misalignments can destroy yields and costs. Plus, silicon and traditional materials don't always have the combination of stiffness and low adhesion that you need for reliable long term operation. The biomedical reality. When you put these devices in the human body, you hit a whole new set of problems. Proteins immediately coat device surfaces and alter performances. The body's fluids, changing pH levels, and enzymes relentlessly attack materials, and nanomaterials can trigger immune responses or toxicity. Essentially, the body fights back against these foreign objects. Long term reliability is still uncertain. Mechanical fatigue, surface wear, and material drift can all degrade performance over time. Before MEMS can become mainstream in clinical settings, we need to solve these durability challenges. Now I'm going to be discussing the applications of biomems. One of the most clinically impactful uses is its lab on chip, which is an entire laboratory workflow miniaturized on a single portable device. We're talking channels 10 to 100 micrometers wide, integrating sample prep, reaction, separation, and detection all in one place. The real game changer in this is speed. Pathogen detection with microfluidic PCR, HIV, hepatitis B, Zika happens in minutes, not days, and sample volumes drop from milliliters to nanoliters. That's huge for pediatric patients or in resource limited settings where you don't have access to traditional labs. You can test at clinics, pharmacies, and even homes. But here's the catch: getting FDA approval requires extensive validation showing results are consistent and accurate across thousands of patient samples. That process can take up to 5 to 10 years and cost tens of millions of dollars. That's why only the most promising applications actually end up making it to hospitals. Another major application is continuous health monitoring. Instead of a single snapshot test, these implantable and wearable biosensors give you real time data streams. Take glucose monitoring. Diabetic patients can now see exactly how their bodies respond to food, exercise, and medication in real time. That enables precise insulin dosing and has transformed outcome for millions. Same with cardiac sensors. They continuously track heart rate, blood pressure, even cardiac biomarkers, catching dangerous arrhythmias before they can become critical. Wearables push this further. Flexible sensors on your skin can monitor sweat, temperature, motion, transforming how we manage chronic diseases. The challenge is long term biocompatibility. Implanted sensors need to function reliably for months or years without triggering inflammation. Plus, the protein corona, layers of proteins that coat device surfaces, can alter sensor calibration over time. Most implantable systems currently need periodic maintenance or replacement. MEMS also enable precise controlled drug delivery. Instead of flooding your entire body with medication, you can target it directly to affected tissues. Biodegradable microspheres can release their payload over weeks or months. One injection can replace an repeated dosing. For cancer, you can inject microspheres directly into tumors, concentrating chemotherapy where it's needed while sparing healthy tissues. For diabetes, imagine a closed loop system that releases insulin in response to glucose levels in real time. The problem is controlling degradation inside the body. Temperature, pH, enzymes, and mechanical stress all vary. That makes it hard to achieve reproducible release profiles across patients. Here's where it gets really powerful. Single cell analysis. MEMS lets you isolate and analyze individual cells independently, revealing cellular heterogeneity that conventional methods miss. In cancer therapy, cells that look identical under a microscope can actually require up to tenfold different drug concentrations to kill. Traditional dose response data masks this entirety. Single cell analysis identifies resistant subpopulations so you can design combination treatments. This is where personalized medicine becomes real. The barrier to clinical adoption is handling data. Single cell studies generate millions of data points per patient. You need machine learning to extract actionable clinical insights from all that information. Why does all of this work? Because cells are up to 10 to 100 micrometers, and enzymatic reactions happen in nanoliters. When your device operates at the same scale as biology, you achieve precision and sensitivity that macroscale devices simply can't. And this is the fundamental advantage. So, where are we now? Mature technologies like continuous glucose monitors are deployed and refined, but most complex multifunctional MEMS are still in research labs or early clinical trials. Manufacturing scalability and system integration remain the major barrier to widespread adoption. MEMS and biomems represent the intersection of engineering and precision and the medical need. We've solved the physics, we've proven the concepts, but translating these devices from labs to clinics requires solving manufacturing, regulatory, and biocompatibility challenges. Over the next decade, we will definitely see breakthroughs that make truly personalized, miniaturized medicine the norm rather than the exception.
But the story of MEMS doesn't stop at biomedical applications. There are many more of them, for example, Internet of Things devices, switches, and sound acoustic wave devices. However, before that, we would like to introduce you to the team of researchers whose article titled Development Trends and Perspectives of Future Sensors and MEMS and NAMS would guide us through the mentioned MEMS applications. As Joe and co-authors point out, vertical, acoustic, and gas sensors are three main major types of MEMS sensors in terms of applications in the Internet of Things. In general, MEMS accelerometers measure acceleration by detecting how proof mass and its supporting structures deform under external force. This deformation is then converted into an electrical signal. Let's move on to discussing the accelerometer types. First of all, we have resonant accelerometers that use vibrating beams whose resonance frequency shifts when stress from acceleration is applied. Piezoelectric accelerometers use piezoelectric materials that generate voltage when deformed by acceleration-induced deflection of the proof mass. You can see the example of the structure of piezoelectric accelerometer on this illustration. Piezoresistive accelerometers rely on materials whose electrical resistance changes when strained. Acceleration alters the beam's resistance, which must be measured using external voltage. And finally, we have capacitive accelerometers, ones that detect acceleration by measuring changes in capacitance caused by displacement of the proof mass. So on picture A, you can see a resonant accelerometer. You can see microfabricated structures that drive and sense electrodes, a proof mass connected to resonating beams, beam 1 and beam 2, and notch flexures guiding the motion. On picture B, you can see piezoelectric accelerometer. In particular, what you see is a symmetrical mass spring structure, piezoelectric elements, the small dark rectangles, and also output diagrams showing voltage generation from deformation. And on picture C, you can see piezoresistive accelerometers. In particular, what you see is a proof mass at the end of the slender silicon beams, piezoresistors embedded in the highly doped regions of the beams, and a fabricated MEMS structure. But we know that since real-world acceleration often comes from changes in direction, this is the perfect moment to introduce our next sensor, the gyroscope. Gyroscope is the sensor aiming at measuring angular variance or angular rate based on the Coriolis force. Before we dive into gyroscopes, let's quickly demystify the so-called Coriolis force, which is simply a very real effect which makes motion appear to curve on rotating planet, pushing beams, currents, and even airplanes to the right in northern hemisphere and to the left in southern hemisphere. In practice, the gyroscope first establish controlled vibration and then rely on rotation causes, and then any rotation causes the Coriolis force to push part of the structure in the secondary, perpendicular direction. Resonant gyroscopes use structures like vibrating disk with two resonant modes. The disk is driven in one mode, and the rotation transfers energy into the second mode, causing the vibration pattern to rotate. Measuring that angular shift gives the angular rate. Vibratory gyroscopes use multiple frames: a drive frame that oscillates, a Coriolis frame that responds to rotation, and a detection frame that remains still until the rotation occurs. Angular motion forces the detection frame to move sideways, changing capacitance in a measurable way. So now we know about these systems, how the system work, and how they monitor things like imbalance or impact in Internet of Things. Let's mention acoustic and gas sensors before we move on to the MEMS switches and surface acoustic wave devices. MEMS acoustic sensor is a tiny microphone that detects sound by converting pressure-induced vibration of flexible membrane into electrical signal. Moving from acoustic sensors to gas sensors, gas sensor is a miniature device that detects specific gases by measuring change in materials' electric properties. For example, resistance shift when gas molecules interact with its sensitive surface. This gas sensor consists of silicon-based microplatform with integrated nickel microheater and zinc oxide nanostructured sensing film supported by silicon oxide layers and patterned electrodes. Now, let's switch to MEMS switches. MEMS switch is a tiny movable structure like a beam or a plate that physically makes or breaks the contact when activated. Instead of straining electrons through semiconductor channel, MEMS switch literally connects or disconnects two points in the circuit, giving it superior performance in low-power devices and precision signal routing. Surface acoustic wave devices are electronic components that use sound waves traveling along the surface of a solid material, usually piezoelectric crystal, to process the signals. This design enables low-power, short-range communication, which makes surface acoustic wave tags ideal for applications like weapon tracking, humidity sensing, and automated traffic or assembly system. In particular, you can see the example of surface acoustic wave devices on the illustration. So now, let's move on to future perspectives. Looking ahead, MEMS will evolve by tackling the challenges we've seen throughout this report. For example, stiction will drive the development of new coatings, 2D materials, and smarter surface chemistries, while biomemes move towards self-calibrating following resistant sensors and closed-loop drug delivery systems that respond to real biomarkers. Optical actuation, introduced by Wang and co-authors in 2025, is expected to expand from powering single micromachines to coordinate entire swarms of wire-free microrobots. In IoT, Zhu and co-authors envision self-powered sensors that harvest ambient energy and integrate multiple sensing modes with onboard AI. MEMS switches and SOC devices will push into 6G and 7G frequencies, enabling ultra-efficient wireless communication. In future fabrication, guided by ideas from Wu and co-authors that they expressed in their research in 2011, and Kamar and Shamsi may rely on self-dissolving sacrificial layers, better bonding, and even accessible desktop-level prototyping.
In conclusion, MEMS are becoming an important area of biotechnology because they offer small, precise, and efficient ways to interact with the microscopic world. While the technology still faces challenges such as fabrication limits, material wear, and long-term reliability, the progress made so far shows real promise. Achieving this future will require cooperation between physicists, engineers, biologists, and material scientists. With steady development, MEMS will move from experimental systems to useful tools that support future research, diagnostics, and technological innovation.